We're going to tackle a difficult pulley problem using forces. So we're given that we have a frictionless pulley, meaning that the wheel itself is frictionless. There are two masses involved. M1 is hanging, M2 is on the table. M1 falls under the influence of gravity, drags M2 along with it. There will be friction between M2 and the table, though. It's only the pulley mechanism itself that is frictionless. Okay, so let's rewind this and put the drawing over in the corner. Now we're also given the two values of the masses, so M1 is 1 kilogram, M2 is 4 kilograms, and we're told the coefficient of kinetic friction between M2 and the table. It's kinetic friction in this case. We're only doing the analysis of this acceleration while M2 is moving. So you can imagine once M2 has started moving, we want to know its acceleration. We also know that F net equals ma. We have an expression for kinetic friction and an expression for the weight. We'll use all of those. The first step in doing a problem like this is inevitably drawing the free body diagrams. You should be pretty good at this by now. Let's tackle mass 1 first. Mass 1 only has two relevant forces acting on it. One is weight pointing downward, so we draw our dot, draw an arrow downward for weight. The other is tension pointing upward. You can see that the weight vector is larger in magnitude than the tension vector. That has to be the case. We know that M1 is accelerating downward. Okay, that's our free body diagram for M1. Let's put that over here for later. What about M2? Well, it's going to be more complicated because it has vertical and horizontal forces, so we'll start with the weight. That's always the easiest one. Weight points down. The normal force from the table points up. Those two should be equal in magnitude and opposite in direction. After all, there is no acceleration in the vertical direction for mass 2. What about in the x direction? Well, the tension points to the right, the force of kinetic friction points to the left, and it must be the case that tension has a larger magnitude than kinetic friction. Mass 2 is accelerating to the right after all. Those are our free body diagrams. And those will help us to decide what forces are relevant when we're trying to calculate the acceleration of mass 2. So first let's consider the forces acting on mass 1. We'll circle them over here on the left. It's just the tension and the weight. So we can write out that the net force in the y direction on mass 1 is Fy1 equals the vector sum of the tension plus the weight, both subscripted 1 for mass 1. There will be multiple tensions and weights, so that's important. Well, we can substitute in for Fy1 its mass times its acceleration, right? F equals ma. So we can rewrite that m1 ay1, where ay1 is now the acceleration of mass 1 in the y direction, equals t1 minus m1g. All I've done on the right-hand side is substituted in minus m1g for w1, realizing that the weight has to point in the negative y direction. So that entire boxed expression only applies in the y direction for mass 1. We'll do the same sort of thing now for mass 2. So now let's move and analyze the horizontal forces on mass 2. Well, in that case, Fx2, so in the x direction for mass 2, is the vector sum of the tension on mass 2 and the force of kinetic friction acting on mass 2. Well, in that case, again, we can substitute F equals ma on the left-hand side, put in mass 2 and acceleration 2 in the x direction. On the right-hand side, we have tension 2 acting on mass 2, and then we've substituted in the expression for kinetic friction. That involves the normal force on mass 2, N2, and the coefficient of kinetic friction, mu sub k. That last term has a minus sign out front because clearly from the free body diagram, the force of kinetic friction is acting in the negative x direction. Now to proceed, we actually have to work out an expression for N2. Well, we can do that by considering the vertical forces on mass 2, right? So let's consider the vertical direction there. The total force, Fy2 in the y direction on mass 2, is the sum of the normal force and the weight force, both added as vectors. Well, in this case, we know that the net force in the y direction on mass 2 has to be 0, right? Mass 2 is not accelerating up or down. It can't possibly be, or else it would move off the table or move down into the table. No way is that happening. Therefore, 0 equals the sum of N2 and the weight, which is negative m2 times g. All right, we can solve for N2. N2 is just m2 times g, and now we can take this expression and plug it into this expression here. Essentially, we're combining the vertical and horizontal force equations for mass 2. We do that, and we get this boxed expression, m2 ax2 equals t2 minus m2 times g times mu sub k. Alright, we've made good progress, but we still need two more pieces of information before we can actually begin to solve these equations. One is something that comes up in a lot of pulley problems, and that's that the two tensions are equal in magnitude, so T1 equals T2. Moreover, the sign is correct. If we think about it, the tension acting on mass 1 points up. That would be positive for mass 1. the tension acting on mass 2 points to the right, that would also be positive, so we don't need to worry about any pesky negative signs hiding in there. The other piece of information involves the accelerations. If you think about it, as long as the rope remains taut, but doesn't break, doesn't get compressed, anything like that, it must be the case that the acceleration of mass 1 and the acceleration of mass 2 have the same magnitude. If they didn't, the distance between them would gradually change, meaning the length of the rope would change, and we're dealing with ideal ropes here. We don't worry about stuff like that. So the magnitudes of the accelerations are the same, but what about the signs? Well, clearly the acceleration of mass 1 is negative, right? It's moving in the negative y direction. The acceleration of mass 2, however, is positive. It's moving in the positive x direction. So the relationship between the two accelerations is that they're equal magnitude but opposite sign, namely ay1 equals minus ax2. It's important to get that sign right, or else the algebra won't work when we try to combine these equations. So let's put all four boxed equations up near the top. The easiest way to solve this system is actually to just subtract off this second one from this first one. So let's do that first, and then we'll worry about the tension and acceleration constraints. So we do that, and we get this long expression, m1ay1 minus m2ax2 equals t1 minus m1 times g minus the quantity t2 minus m2g mu sub k. I think I said all that correctly. First step, we want to substitute in minus ax2 for ay1. After all, we're trying to solve for the acceleration of mass 2, so we'll do that. And we'll rearrange things nicely on the right-hand side because you can see now on the right, I have this term T1 minus T2. Well, that's going to be 0, right? We just said that two tensions are equal in magnitude and have the same sign, so that simplifies things considerably. We pulled out a power of negative ax2 on the left. Well, that's nice because that's what we're trying to solve for. Everything else we know. It's masses, little g, or the coefficient of kinetic friction. So we'll just rearrange and solve for negative ax2. And now we'll solve for positive ax2. And sure enough, we have a closed form expression for ax2. Not so bad. The last step is just to put in the numbers. So we know that little g is 9.8 meters per second squared, and we're given the masses and the coefficient of kinetic friction. Do all of our math, simplify things a little bit, and we find that the acceleration of mass 2 in the x direction is 0.392 meters per second squared, or to two significant digits, and putting it back in vector notation, a2 equals 0.39 meters per second squared times I hat. The nice thing about pulley problems, and maybe the only nice thing, is that once we know the acceleration of mass 2, we immediately know the acceleration of mass 1. We have the same magnitude, but it'll be in the negative j hat direction, so a1 vector equals minus 0.39 meters per second squared j hat.